Hi guys, I'm back. This is going to be it's a video to answer some questions that was in my comments. There's two primaries and a couple other questions in there. I've got one of my viewers who's new to my channel asked a question. We're seeing part of a schematic of a Philco 90, and it's on my monitor, so it's going to blink a little bit because of the difference in frame rates between the camera and the monitor, so bear with that. But the question was, in a Philco 90, the detector tube is nothing but a 27 triode, and how does it work? Because the plate is connected to ground with the cathode. In other words, the plate and the cathode are connected together and they go to ground. So how's this working? And I want to do a video on the various different types of detectors here in the near future, which I'll go over a little quicker or a little more deeper on this. But it's actually a pretty simple circuit. Back in the day, like when this radio was made back in the very early 30s, tube selection and number of tubes that were available were not a great number. In fact, if you look at tube manuals from about that period, you will find that it's pretty lacking on tubes. So this particular radio actually uses, other than the rectifier tube, which is an 80, it only uses 3 different tubes. The front end is entirely made up of 24s. Most of the audio is made up of 27s, except for the final output, which I think is either a 41 or a 47. The local oscillator is actually a 27. So type 27 triode. So, but they didn't have a lot of selection, so they did things a little differently. And you can make a diode tube out of any tube. You can make it out of a triode, turn it into a diode. You can turn a tetrode, a pentode. I don't care how many elements is in it. You can turn it into a diode. I don't know why you do a pentode that way, but it's a rather expensive tube to be turning into a diode. But what they've basically done is, by tying the cathode and the plate together, we've just turned that into one element. In other words, basically we're just ground the plate off. We don't care about it too much, so we're just going to get rid of it. By grounding it, we have gotten rid of it. It will stay negative, as with the cathode, at all times. So that leaves the actual operation of the tube is just the grid, and the cathode is really, because the grid's quite a little bit further away from the plate, so it matters not. And the plate's not designed to actually emit electrons, although it can. The cathode is the guy who actually emits electrons. So really what we're doing is we're grounding the plate out to get it out of the circuit completely, and we're just working with these two. Now we have just 2 elements, a diode. Now how it works is we've got a signal coming in here, and as you know, a signal is just a sine wave. It goes positive, then it goes negative. Well, when it's going positive, in other words, when this is positive here and negative here, so that it's going positive, that makes the grid positive respect to the cathode. At that point, we get electron flow. Electrons go from the cathode to the plate, flow through the circuit, they come down here, that signal goes through this pathway here, up through to my volume control, right here, feeds out and goes to my detector amp, and then on from there it's amplified and on to the first audio. On the next half cycle, when it's going negative, this is negative and this is positive. At that point, the grid is negative with respect to the cathode, and nothing happens. Nothing goes through. Typical diode. So the only thing that's going through here is these positive halves that are making it through. Only when this is positive, only on that part of the cycle, does it go through. The negative half doesn't. Now the rest of the circuitry, we have a load resistor here which feeds down and goes to is feeding our AVC circuit. That's all this is doing here. It's feeding the AVC. The capacitor here and coupling with the load resistors, part of them is your filter that filters out like I talked before, and then you've got your second filter cap here, the decoupling cap that's here, that will bleed off any left of the IF energy, and that's it. That's how it works. Just the simple fact that all I was doing here, all they were doing was getting rid of the plate. The best way to do it is take it to ground or tie it to the cathode and take it to ground. You have your load and your filter capping here, filter circuits and load circuit for the ABC. Again, the signal makes it through, it comes through this line up to through the grid load resistor, through the coupling cap, and to my grid. Control grid. On the detector amp, they're needing the detector amp because this will be not a strong signal and they want to strengthen the signal, so it's really an audio amp at this point, but they call it a detector amp, and then it goes to the first audio, then to the final. So I hope that kind of answers your questions. There are various ways of doing this. You can tie this in like this. There's times when they just would on these actually ground the cathode or ground the grid to the cathode and just let the cathode and the plate be the diode circuit. There were some radios where they actually took the grid and hooked it to the plate. Those are very rare. Generally the more common one is to get rid of the plate like this. So like I said, I'll go over a video on detectors sometime in the future because there's various different types of detectors, but in this case all we're doing is we're really concentrating just looking at this junction here between the cathode and the grid. And when the grid goes positive, then we get flow. When that grid goes negative, nothing happens. So that's how that works. Now on to the second question, which Phil posed, Steel City, my good friend from across the pond, and that was talking about pi filters. And we're going to talk about a pi filter mainly in a power supply on the high voltage secondary or high tension, which by the way, Phil, in the engineering circle we do call it high tension. In the tech or radio repair circle over here, it's more just called high voltage secondary. So we're going to look at some various things. Alright, we're not, I already went over basically what happens in a full wave and how it works. The center tap is our neutral or common, so part of the time we've got a loop going through this. When this is positive, we get a loop through here, we get a flow going through this down to the ground, going through our radio over here and back to the cathode. And then when this side's positive, the same thing happens. So we won't concern ourselves. I'm using something like an 84 tube in here. Basically it has a cathode that is heated with a heater, as opposed to, we already talked about where like a type 80 tube where you just got the filament. How does that work? We already discussed that. So anyway, at this point, if we put a scope on here, since it's a full wave, we're going to see humps. The positive half cycles is all you get through here. And since it's full wave, they just are real close together. Now if it was half wave, then you would lose part of these. You'd lose like this one and this one. So you just loop up, flat, loop up, flat. With a center tap transformer, dual diode on my rectifier, I can get a full wave. Now, at point 2, if I hooked a scope here, this is with no load. In other words, it's not hooked to a radio. It would charge the capacitor up and then just flatten out. And it would stay that way. That's with no load at this point. If I put a load on for number 3, in other words, I go ahead and hook it to a radio, or hook the radio up, or put all the tubes back in, or whatever. So now I have a load on here. Then what it does is it comes up, peaks out with full charge on the first peak here, but with the load it starts draining off that cap a little bit before the next peak comes along and starts charging the cap back up and down, up and down, up and down, up and down. That's with the load, and it's your ripple. You will have some ripple. Now, what about this point here? This is a pie filter with a choke. This is usually the way I like to build power supplies if I have chokes available. Or I might even wind my own. One day I'll talk about how to wind a choke. It's real simple. Or you can use, be surprised what you can use for a choke. But in any case, this is with a cap, choke, cap. No load. We charge up. This time 2 capacitors are charging. We're drawing current through. And due to the fact I have a choke here, it will actually overshoot just a little bit and then come back down and stay steady state. At 5, I put the load on. We get a little bit of a curve winding up because of the choke, and then it goes and gets a little bit of overshot. This is just when the first power up, and then it will stay very, very steady, even with a load. Now, what if I change this out and put a resistor? You'll see in a lot of radios that you have a cap resistor cap, generally like a 1K or 2K resistor in here, and a couple filter caps. Well, even with load, without load it's flat. With load you will still have a little bit of ripple. Now most radios it matters not. It makes no difference. And this ripple is actually can be reasonably small depending on the size of the filter caps. With the choke, we generally use and get by with like 8, 10, even 4, 5, 6 microfarad caps on here. As the radios got newer and stuff, they actually put a little bigger caps on here, but generally not huge because they had the choke. The choke literally chokes AC. It does not like AC at all. And I'll go into more in depth in why that is, but it has to do with the counter EMF. So it does not like the fact that there's a change in it. It likes steady state. So any changes it tries to get rid of, and it will get rid of. So I can get by with much smaller caps for my filter caps with a choke. With a resistor, I have to really more than triple the size of these caps. And generally what is done is you'll have like maybe a 30 microfarad here and put in something of the nature of a 40, 50, or 60, or even 100 microfarad on the output. You can get by with that because the resistance keeps from, when it initially turns on, keeps from that pulling too hard on the rectifier and possibly doing damage. So with that resistor in there, that kind of surge protects a little bit so you can get bigger caps. So you'll have a little bit smaller cap here and a little bigger cap here. And depending on the size of these caps will depend on then what size of an amount of ripple that you have in here. Because the resistor is doing absolutely nothing. It's a passive component. It just drops some voltage is all it's doing. And that's it. So it's actually the cap's doing something. Where you got a choke, then you've actually got all three elements doing your filtering. Now the resistor does create a time delay, which is how we actually work with a ripple and how quickly we discharge these caps. So that's the only other thing it has working for it. But you will have some ripple. You can increase the size of these caps. You can work real hard at trying to reduce this, but there is a certain point that you can't go beyond, or it just, you get no more return. The best way is to go ahead and double this. If you're getting to that point and you still want to reduce the ripples, put another resistor in and another cap, filter cap. So you have double pi, a 2 pi circuit, which then will actually do a better job of reducing this. So I hope that kind of answers exactly. Basically all it's working here is I feed a signal in, I charge the cap up, that starts filling in these areas. With a load on there will be some drain off. That's why I have the second filter plus the choke. The choke will kind of help out a lot of that drain off and smooth that out, along with coupling with the last cap that's in the pi, which actually then will be also charging up and staying charged, that will also help reduce the drain off that you would have on the ripple for whatever might actually make it through the choke. Will be very small, and this final filter cap will be easily, even at 10 microfarads, large enough to easily clear and bring that out to a very flat line, pure DC. Now this brings up one other question that was in my comments a long time ago and I hadn't had a chance to get to it. On building power supplies, do I need a bleed resistor? And the answer to that is no, as long as this is a permanent fixture of a radio. In other words, this is the power supply in a radio. Because the radio itself, when I shut the power off, the tubes stay hot, they still conduct. They will quickly drain these caps off. But if this is a bench power supply, then yes, I need a bleed off. And there's a formula for that, and in a video on power supplies I will present that then. But if it's you're building it for a radio, maybe building your own radio or building a power supply, that's going to be permanently fixed in the radio. You do not need bleeders. So I just wanted to bring out that point. Alright, now I think I got a little bit of time to answer a couple other questions. One was by Art, and let's see. Okay, really, you asked me, so when a tube amplifies a signal, it's always inverted. And yes, it is. As a standard amplifier. If a cathode follower amp, which is not really amplifying the signal, it's pretty much less than unity, then in that case, no. They stay the same. But when you're running just a standard amplifier tube, amplifying signal, it does invert. So the output is inverted to the input. And one last little thing here, and I'm going to try to answer this quickly. Of course, like on your question there, Art, again, The drivers here are cathode followers, so what goes in the grid is not, and comes out the cathode, is the same. They're not inverted. But what on these tubes here, or this tube here, what goes in the grid will get inverted coming out. But so amplifier tubes, this is an amplifier, this is an amplifier, and this is an amplifier. Even though this is classified as an amplifier, cathode followers are, they're not really amplifying. They're actually reducing just a little bit of the signal strength. So regular amplifiers always invert. Now, to answer Tom's question, does the phase inverter, phase changer, does it really become the main guy for trying to keep everybody balanced here? In other words, is it its job to try to balance everything? The tube itself, no. Although you want it operating good, but no. Basically, how I keep the signal strengths pretty much in tune as far as strength or having balance is by this resistor right here, this 390K. And what its job is I'm bringing out a signal from here, coming out. Now if I follow it straight through, it comes and goes to this grid, so it has a certain strength. Alright, if I would not have this 390K and I fed that same strength signal into this grid, since this is an amplifier tube, then it's going to amplify that signal. And depending on the tube, depending on how it's biased and so on, you know, it could be 10, 20 times the size difference between this signal here feeding into the grid and this signal coming out here. So how do I do that? What do I do about that? Well, what I do is I put a resistor in here so that this grid is getting a lot less signal than what this grid is getting. That's how I'm doing that. So that's what that 390 is there. If there's anything that's balancing those two signals, it's this 390. And that's what its job is. It'll reduce the signal strength by the amplification factor or the gain of this tube. So that then when this tube amplifies and the signal comes down here, these two will be as close as possible in size. Now, we feed them through a buffer and we go here. What about balance? Is there anything else in this circuit or any push-pull circuit that really does work as a true balancing piece of equipment or element? And there is the output transformer. Even if these signals coming from here are off a little bit, say less than 20% off, just to pick a number, but if they're off a little bit, and trust me, they will be, okay, this output transformer, by the fact that it's center tapped, it's designed for push-pull, will actually balance it and will take care of it. I'm not going to get into it right now because I haven't got into push-pull, but suffice it to say that it's doing it because of the fact of that center tap being neutral. Alright, at the center tap, remember when I was talking about push-pull a little bit, they cancel, the signals cancel. Well, if there's a little bit difference in signals here, coming on the outside windings here, coming from the plates of these two tubes, then that center becomes a little bit unbalanced, or appear to be, and at that point the transformer will cancel those two and finish off the canceling. Now, that's up to a certain point. At a certain point, it can't do that anymore. And then you'll start getting some distortions. But until you hit that point, it can actually deal with it. All right? And that point really works out to be something that's easily dealt with. The point works out, I picked 20%. That varies depending on what type of push-pull amplifier we have here, the tubes we're using, the transformer we're using, the whole 9 yards. But as long as I'm below that point, which I will pretty much always be, no matter what age the radio is, no matter how long it's been operating, no matter what, we're perfectly fine. Worst case scenario, when you're below that point, all ends up happening is that these two are just slightly out of balance, again, less than 20%, your output will have a little bit less wattage. Not a lot, but a little bit. So, say I'm supposed to have 10 watts out to that speaker at full volume. Remember, when they're sitting here putting the specs in there, and they're telling you it's a 10 watt output, that's with full volume. That's with full signal going into these tubes. So at full volume, if I'm supposed to have 10 watts, if they're less than, up there close to that point of, roughly 20% out of balance, then it'll be around about 9.25 watts out, roughly. So these are all rough numbers, and they all vary a little bit. That percentage varies a little bit. There's a lot of variables in here. And at some point we'll go over that. But in a simplified explanation, the real balancer is the output transformer. The buffers take care of any little minor signal degradation that's happening from this circuit here in the phase changer circuit, such as if that resistor starts going out of spec, which we all know can happen. So these can actually take care of that a little bit, up to a point. But tubes age differently. So when you start off with a brand new radio back in the day, everybody's all equal and everybody's happy. A year later, one of these tubes may not be putting out as much. It's always going to be less than that point. Unless something really goes wrong, like a tube loses its filament and dies, or it gets an internal short, it gets gassy, or something like that, you generally are not ever going to notice these age, that you're going to have a problem. So I hope that kind of answers your question. This has gotten long. I think I covered most of the stuff I wanted to cover. We'll try to work on, some more on this schematic. We'll cover the power supply mainly in the iTube, and in the next video, unless more questions pop up. I hope I explained the stuff better, or at least so everybody can kind of understand. And I will try to answer some more comments as far as typing in something. But I do read your comments and acknowledge them. I thank you guys for your comments. They are an inspiration to me. And thanks again for welcoming me back and everything. Again, this week I'll be starting back over there on that remodel, and but hopefully it won't be as tiring, and maybe I can get some videos in the evening and stuff. Oh, for any questions or anything else, last time I left you off, we was working on this radio, this Philco. I've been getting it pretty much finalized, polishing. It's not perfect. I do have one little rust spot, which never fails. It seems like every radio I've had, except maybe one or two, that no matter what the chassis can be really mint condition except for one stupid little rust spot. So I'll probably just coat that with something to keep it from ever re-rusting, but leave it that. I mean, there's some other little spots. These up here I don't worry about, because there's the coming out here is the push buttons, and then you got the dial on here. By the time you get all that in there, this is never even going to be seen. This is only it's kind of sore thumbed on me, but anyway, that is where that's at right now. It'll start going back together, so look forward to some videos on it. Seeing that, the one thing that I haven't decided what I'm going to do with is the transformer actually had a cover over it, something like this, and this cover, due to heat and time, I believe it was painted. I tried polishing it here, but it really, I don't know, it just is not going to turn out. So I may just leave it, kind of, get it clean, but leave it, or I may paint it, some silver paint. I don't know yet, for sure. Give me some comments what you guys think. So anyway, that's that. Oh, here's the scope. It's working, so thought I'd show you that. It still has a little problems in the switches themselves. They're a little dirty, but they're sealed. I don't know if I can actually completely dismantle them by pulling them off the circuit board. They've got plastic covers over them, which was not allowing me to get any type of cleaner in them. So if they start getting a little bad again and really getting funky, I may go ahead and pull that board back out and just take them off the board. They're only connected on by the ground points and a couple connections, and take them off, and so you can see some of the flakiness here with this line right here. But if I mess with the switch, it cleans it up a little bit and stabilizes it out. I may have to try to see if I can get them apart and clean them. Trying to replace them is probably not going to happen anytime soon. So anyway, that's where we're at. Sorry for the long video. I hope I answered some of your questions. If not, just let me know, and I'll let you. I'll go over it again and go into more detail. We will go into some detail, a little bit of detail with this power supply here. Again, probably not a lot, but we will go a little bit. And so anyway, until the next video, thanks for watching, and I'll see you on the next one.